So let's start. Good afternoon to you all. Today we will be discussing about the fundamental concepts of learning vector quantization, uh, support vector machines, and then regression, and then we will be focusing on the k nearest neighbor classifier. So these are the fundamental concepts linked with some techniques that are quite frequently used as part of um, machine learning systems. Therefore, while we have been discussing different learning-based techniques so far, these concepts too also have some role to play in the design of learning-based systems. Therefore, we are focusing on the learning vector quantization, support vector support vector machine, then regression, and k nearest neighbor. So in this discussion, we will be focusing on how these four different techniques work, the basic way to do their programming by the use of MATLAB. So we also covered so that you all can try in the MATLAB domain and then develop some systems based on it. Now, learning vector quantization is based on learning vector quantizer. Now, first we should refer to the term vector quantization. Vector quantization is linked to a sample space that is subdivided to a number of distinct regions that can be a part of a classification or regression process. And for each of such a region, a reconstruction vector is defined. A vector thus defined forms a vector quantizer or vector quantization, or the process of defining such a vector forms the vector quantization. So when you subdivide the sample space to a number of distinct regions for carrying out classification and recognition, and you link a vector to it, then you have the vector quantization process. Now, a vector quantizer, a vector quantizer with minimum encoding distortion is called a Voronoi or a nearest neighbor quantizer. So when the term Voronoi comes, that means we are referring to a nearest neighbor quantizer. The collection of possible reproduction vectors can be called to be a code book that will have all the quantizers, and its members are called the code vectors. Therefore, the vector quantization process shall be the formation of a number of quantization vectors, and then forming a code book where all the quantization vectors shall be stored. These will be linked to some sample space, and then the sample space subdivided to several smaller parts can be a part of the process of doing a classification or recognition. So this particular diagram here shows that this is a Voronoi or a nearest neighbor quantizer. Now, this particular nearest neighbor quantizer shows us the location where the subdivided sample space shall be. Now, learning vector quantization and SOM, self-organization map, is very closely linked. Both are discussed together. last time, since we have covered SOM, therefore it's quite logical to uh, discuss learning vector quantization as its follow-up. A SOM can be used for dimensionality reduction from a large data set. The SOM is capable of generating representative vectors. Now, these representative vectors can be called uh, codebook vectors. So we have just referred to a sample space be subdivided to several smaller parts, and a vector could be linked with each of these subdivided parts. Now, this subdivision can be done by the help of a SOM. The SOM can generate generate representative vectors. Now, these representative vectors can denote the subdivided sample space. And then these will be called codebook vectors. Codebook vectors provide an approximation regarding the several subdivided parts constituting the sample space. This is the basic concept behind vector quantization. So you can use a SOM for subdividing the sample space to several smaller parts, and these several smaller parts can have a representative vector, and these representative vectors, when are stored in a database, that particular database can be called to be a code book, and these vectors then become a code book. Uh, can be a set of codebook vectors. The codebook vectors are generated through vector quantizer. So SOM can be a very reliable means of generating these vector quantization process. So here is a very simple depiction of how we can link see, or how we can visualize the total picture. So here we can take an encoder-decoder model. So here we have a pattern vector being passed through an encoder C of X that will be generating a code C of X. That particular code can go through a decoder that will form X dash of C, and that particular vector shall be called a reconstructed vector. So vector quantization process is well simplified by this particular encoder decoder representation. Now there is a rule called the generalized Lloyd's algorithm, through which this encoder decoder model can be carried out. So the most necessary conditions for minimizing the expected distortion D in general situations are covered by two conditions. The first condition is that you have a sample vector, or you have a pattern vector X. You choose a code C is equal to C of X to minimize the squared error distortion given by this particular norm, X minus X dash of C norm square. Then given the code, the second condition shall be, given the code C, compute the reconstruction vector X dash of C such that the centroid of these two input vectors X satisfy the condition 1. So these two are called the generalized Lloyd algorithm. Now, one more thing that comes to the consideration shall be how you subdivide the neighborhood. So this is called the Voronoi tessellation, a vector quantizer with minimum encoding distortion is called a Voronoi quantizer or a nearest neighbor quantizer. The input space is subdivided to a set of Voronoi or nearest neighbor cells, and each containing an associated Voronoi or reconstruction vector. So you can here find that the Voronoi quantizer shown by the blue will be approximating the the neighborhood that uh, the quantized vector shall have. So each of the red dots shall represent a codebook vector denoting a particular class, and the dotted lines will represent the neighbor to which the codebook vectors or the dotted order or the red dots are confined to. So this shows how a Voronoi tessellation is done in the vector quantization process. Now we can find quite frequently learning vector quantization being a part of the SOM. So when you have a learning-based process driving a vector quantization, that part is known as learning vector quantization. Now, learning vector quantization is a learning-based supervised version of the vector quantization. It uses label data. The learning technique will give it all the relevant support required to generate or to place the class vectors in such points where once you finish the learning process, the results and the reliability shall be better than that generated by the SOM. So this finally results in a better quality of classification. So hence we find that when you use a learning vector quantization, that means you are planting a supervised process with the unsupervised SOM so as to make the classification, reliability, and the quality of recognition become better. So the whole flow can be something like this. Here you can think like that the SOM will be there, you will be feeding the pattern, then you will be doing a feature selection. Once you have the features generated, that will be passed on to a learning vector quantization process. That particular learning vector quantization stage will have feed from the label data. And from that, you can generate the classification decision. So this is the flow, this is the workflow through which learning vector quantization is linked with SOM and how it works together with SOM. So the learning vector quantization network can be seen as shown in this particular diagram. So here we find that till the middle layer, till the second layer, this part shall be the SOM. So here you have the unsupervised learning going on. The last layer shall be a supervised layer. So we can find here that learning vector quantization is a supervised learning technique that will use class details level class data to move the Voronoi vectors slightly so as to improve the quality of a classifier decision region. So you can have a better classification decision coming due to the supervision, due to the supervised learning that is used at the last layer of the learning vector quantization network. Before the last layer, till the middle layer, you have an unsupervised training going on. That shall be part of the SOM. The SOM here shall be generating the features, and the features when are combined with the label data in an unsupervised layer will make the recognition reliability go up. So this is the primary benefit that we get from the learning vector quantization. So you can have the learning vector quantization steps. You first have a sample vector x. Now, if the class labels of the input vector x and a Voronoi vector w both coincide, both say yes, then the Voronoi vector w is moved in the direction of the pattern vector x. Now, if the class label of the input vector x and the Voronoi vector w disagree, the Voronoi vector w will move off from the input vector. Now let wi1 j is I is equal to 1 denote a set of the Voronoi vectors, and let the x j with a dimension of n with I is equal to 1 denote a set of input vectors. Suppose that the Voronoi vector wc is the closest to the input vector xi. Let wc denote the class linked with the Voronoi vector wc, and lxi denote the class level of the input vector xi. The Voronoi vector wc is adjusted by following the following rules. So Lw of c will be Lxi when Wc n plus 1 will take the value of the present weight Wc of n plus the learning rate and the difference between the pattern vector and the Voronoi weight vector, such that this learning rate is a fraction between 0 and 1, and if not, the second condition shall be there governing, and rest of the Voronoi vectors shall not be changed. So this will be the process through which the learning vector quantization shall work, shall function. Now let's see a learning vector quantization example. Now we have here a learning vector quantization network. We have the weights W of 1, W of 2. So the weights are here clearly shown. So 0, 0, 1, 1, minus 1, 0, 1, 0, 1, and these so we now have a few queries to see to meet the total number of classes this learning vector quantization has, the total number of subclasses, to which class that a subclass belongs. Now, since W2 is a 5 by 3 matrix, this learning vector quantization network has a subclass of 5 and class 3. So 5 by 3, so there shall be 5 subclasses and 3 classes. Now subclass 1 belongs to class 1. Now there's a reason behind it. We can find the difference between 0 and 1, so that shall be 1. Now if we have the subclasses 2 and 3, we will get a difference of 0 minus 1 minus 0 and minus 1 minus 0. Take the norm, so that shall be also that shall also generate a value, but hence both the subclass 2 and 3 will belong to class 2, and when we take the value of 0 and 0, that is a subclass 4 and 5, we find that from that we generate values of 0. So hence we will find that subclass 4 and 5 will be belonging to 3, and when we get this particular decision, we can build the learning vector quantization Voronoi as shown in this diagram. There is the weight W2 to 1 with a subclass 2, that's for class 2. Here is the subclass 3 for class 2. There is subclass 1, that's class 3, and subclass 4 a link with the weight 4, and then subclass 5 or class 3. So that way, the the Voronoi shall be building up. Now let's find out how the learning vector quantization block in MATLAB will be looking like. Now, in case of MATLAB, we find that the learning vector quantization network is formed first by a competitive layer. So this will be a competitive layer. Here is the pattern feed layer, and the last layer is a purely linear layer. So a pure lin function has been shown. So this one is a competitive layer. The learning in the competitive layer is similar to the ways as a competitive learning is carried out by the function new c. So here you have a competitive layer where unsupervised learning will take place, but in the linear layer there shall be a supervised learning taking place. A transformation is carried out by the competitive layer so as to classify the classes into target groups as identified by the user. So here in the last layer, the user shall be providing or shall be feeding the class data, and that particular class data content shall be taken by the supervised layer to map the patterns and then group them by following the classification logic. So in the last layer, there shall be a supervised training going on, and through which the recognition shall be done. So a more wider depiction where you find that R shall be the number of patterns you feed through the sample vector P. This will be going through the competitive layer, where you find that ndist will be a function that will be used to find the Euclidean distance, and once the Euclidean distance is found, depending upon the value, we will then group the particular sample with the nearest neuron in the SOM topology. That particular SOM topology is here denoted by the S1 block, where a competitive learning will take place, and there a number of competitive neurons shall be grouped. Once that grouping part is complete, they will form a number of feature vectors, and those particular feature vectors shall be used to feed the linear layer, where we will have target data coming from the user specified labeled data. So there will be a mapping between the feature vectors and the labeled data, through which the learning process will be sustained, and a mapping developed through which the recognition or the classification shall be carried out. Now, in case of MATLAB, we can create a learning vector quantization by the use of the function LVQ net. So here is the function. There are three parameters to be passed. So the first parameter shall denote the number of first layer hidden neurons. The second term shall be the learning rate. Default is 0.01. And the last term shall be the learning function. The default one is learn LV1. So these are the parameters, and this is the syntax through which we can create a learning vector quantization network in MATLAB. Now, if we do a classification, or if we use a, a data set linked with the iris of flowers, that can be used to do a classification of the iris flowers. So here we take the data set, and then we here uh, generate a learning vector quantization network with 10 number of middle layers, 10 neurons in the middle layer. Then we have to specify the parameters for doing the training. We will be doing a training for 50 sessions. Then we give uh, then we use the train function to take the net variable, and with it we use the pattern the target. So x will be the pattern and t will be the target. Then we view the network, and then we simulate the response of the network, and then we determine the performance of the network, the classification performance of the network, and then we find out the classification result that is linked with the simulated response of the network. We find that a network structure with a pattern feed block, with a layer here and with a layer there, and a response block shall be generated. Then we will be finding that the learning is quite steady. The learning descends and will be reaching a convergence point fast, but there shall be a number of fluctuations. But by a 50 number of iterations, the network will be stabilizing, and then beyond that, there is no further growth in the network's learning performance. We can uh, from the training and the testing and the validation stages, we can create training, validation, testing, confusion matrices, and from these confusion matrices, we can verify that the network has shown a significant range of performance variations, and the best performance variation and the best performance given is 92.7. So there is the classification performance. So we can see here, or can find out the training time rate of conversions for false positive cases. Then so this can be four different depictions during the training time, validation, testing time, and all of them combined together. So this was regarding the learning vector quantization. Then we come to the support vector machine. Now these are support vector support vector machines are a class of machine learning tools that demonstrate less computational requirements for classification problems. So we have less computational demand. We can generate the classification result, but we will find that here the computational demand shall be less. We will find that there shall be two planes. Here is the first plane, x1, and there is a second plane, x2. We will have here a maximum margin hyperplane, that solid line. We further have a maximum margin shown by this dotted line. Then we have a negative hyperplane. We have a positive hyperplane, and around them we have support vectors. Now in this region we will have a sufficient number of processes giving us the best classification performance. So that is the basic concept behind the generation of support vectors in support of a classification process. Now we can find that the support vector machine is a data dependent classification technique. It is becoming more and more popular. We can find here to be a good classification method that can get rid of underfitting. So where you have a small training error, and you can get rid of overfitting, where you can have small testing error. So it was first launched in 1992, and it has become quite a popular one in all domains of pattern recognition, and was first proposed by Wapnick. So we can have the support vector machine being used for a lot of situations: handwritten digit recognition, spam filtering. Then you need to have data for different classes, but we need to have labeled data. Then once we can train and generate and the support vectors, we can take the test data to do the prediction. Here both the training and testing part are done with supervised learning, but they are all data dependent. We can find that there are corresponding techniques like the nearest neighbor, neural networks, and the decision trees. Now, a very simple classification problem is the binary classifier, where we can have a set of training data with a target for I going from 1 to n, with the small xi belonging to R, that is a d-dimensional sample space, and yi belonging to -1 and 1, which is shall be doing the classification. Shall represent the classifier with a functional representation of f of x, such that f of small xi taking value greater than or equal to 0 and less than 0 when yi is equal to +1 and -1, respectively. So yi when combined with small f of small xi taking value greater than 0 for a correct classification, will group the blue dots and the red triangles, something like this. So this is a depiction of the binary classification. We can also find linear separability. So this is a depiction of linear separability. We have talked about that beforehand, and this part is not linearly separable. We can further go in for the definition of linear classifiers as we have done previously. So this is this small of x, taking the value of w with a transpose t x plus b. This is the equation of the straight line, can be the basis of formation of a linear classifier. So this will be the discrimination boundary. This will be region for one class, and this will be the region for the remaining class. In the 2D two dimension, the discriminant is a line. W is the normal to the line, and B is the bias. W is known as the weight vector. We are all familiar with these terminologies now. So x1 and x2 are the two planes. And then we have further gone through the perceptron classifier, and we have also gone through how the perceptron learning rule is combined with the perceptron classifier to deal with multi-class problems. Now these can be used for generating both linear and non-linearly separable classification. So if we can see it in two dimension, we find that supposedly we start with W taking value 0. Then we go through a cycle of data points x1 and y1. Now, if xi is misclassified when W takes value W plus alpha signum function of f of xi multiplied by xi. So this is a condition that can be linked with a two-dimensional case of classification. We can do it, repeat it till all the data are correctly classified. So before we run the cycle, before we do the update, we find that the depiction is something like this. The discrimination line is staggered close to the red region, with one of the red triangles remaining closer to the blue region. But when we do the update, we find that the decision region formed by this solid black line is coming closer to the blue region, with one point, one red triangle and two blue dots. One red triangle coming closer to the decision region, while we have the two blue dots crossing the decision region. Now, this is due to this particular situation has developed when we have a condition shown below. That means that the training has not reached a convergence limit. So now, if we do the same thing with a perceptron, we can train it sufficiently to lay a decision boundary through which we can properly segment out both the regions and place them in two separate classes. So the blues are in the blue region and the reds are in the red regions. Now here, what we see that the most common thing is that the resultant classification shows us linear separability. We will find that the algorithm will slowly converge. We can find that that the separating line close to the training data. Then we find that here a larger margin is required for generating a generalization, and we should here guarantee that there is less chance of developing memorization. So how we select the best W? So we need to do a number of trials, and when we do a number of trials, we find to begin with that the separation line first falls in the blue region close, then during the next cycle, we find that the separation region is still though is separating out the classes, yet it is closer to the blue part and is far off from the red part. Once the third cycle is complete, there is a slope, and around that slope, we find at one end there is the blue part, and at the one end there are red uh, red samples. And finally, when we run a number of trials and then find that the training has converged to some point, then we find that at some point where the line is placed vertically, both the regions are properly separated out. Now, this is resulting in maximum margin solution, most stable under perturbations of the input feed. So, despite there are multiple variations in the pattern feed, we find that there is a maximum margin generated. Now, this particular maximum margin generation is one of the goals of the support vector machine technique. So we find here that a support vector machine technique will try to generate linearly separable data. So here we will have this particular solid line will try to generate a maximally separable region, which separates out the samples while they are grouped in proper region. A decision boundary shall be laid properly. That will be defined by W transpose T x plus B is equal to 0. There shall be support vectors for the red region. There will be support vectors for the blue region, and all of them will be separated by a margin B by the norm of W. That is the bias normalized by the norm of the weight for that particular region, and the function that shall be linked with it shall be the small f of x, taking the value of alpha I, yi, xi t, then x, that is through which the support vectors are generated or linked, plus b, and this I is summed up for the whole data set, for whole of the sample space. So we find here that the support vector machine technique lays focus on the generation of maximally separable region, through which there is a higher reliability generated in the recognition process. So we can summarize the support vector based classification like this. We can take training vectors xi with I taking values of 1 to 3 till up to L. Let us consider two simple cases. We define a vector y I taking value 1 if class xi is class 1, minus 1 if xi is in class 2. So a hyperplane which separates all data shall be the key for the classification. So the separating hyperplane can be defined by this WTX plus B is equal to 0, and then WTXI plus B when is greater than 0 if xi if yi is equal to 1, and WT xi plus b less than 0 if yi is less than minus 1. So as we have said or have found beforehand, that the decision function will be now will be generated, or will be using the signum function, taking value wt of x plus b, where we have the small x to be the test data, and the variable w and b can have several choices, and those can be selected in such a way that we can lay the plane as per the requirement. So we find here in this case, in the first case, in the left figure, we have laid there a decision plane. The dotted line shall be the decision plane. Yet from the dotted line, there are two more solid lines. One solid line for the triangles, and one solid line for the uh, for the circles, and they are here forming a maximally separable region through which we can have a highly reliable classification performance generated. So how we now generate the maximal margin? We can generate the maximal margin by selecting W and B in such a way that the maximal distance between WT of x plus B shall be plus minus 1. This is called Bucknick's statistical learning theory. So this one, WT xi plus B, taking value greater than or equal to 1 if yi is equal to 1, or wt xi plus b less than minus 1 if yi takes value minus 1. So this is the first postulate of Bucknick's statistical learning theory, and the distance between wtx plus b is equal to 1 and minus 1 is given by 2 by the norm of the weight is equal to 2 by the norm of wt, that the transpose of the weight multiplied by the weight. So this is one more condition, and then the maximum value of 2 by the weight norm, taking value of minimum, the weight transpose dot product with w by 2, so that finally you have a min w of d turning out to be half of w transpose dot product w, subject to yi taking value of w transpose dot product with xi plus b, taking value greater than or equal to 1, that is coming from 1, for I taking values from 1 to L. So this is called Bucknick's statistical learning theory, through which we can find the necessary and sufficient conditions for selecting W and B for maximal margin with support vector classification. Then we can follow that part, and then go for finding the decision function, which starts with a weight that is a vector in a high dimensional space. We may define infinite variables. The dual problem has a minimum of alpha, that is half of alpha transpose q, that is the coefficient, and then one more time alpha minus e of t alpha, subject to a particular condition where this alpha, being the learning rate, is confined to 0 and c, with I taking values of 1 to L, so that y transpose multiplied by alpha is equal to 0, and this q is defined by the term qij taking value of yi, yj, phi of xi transpose, phi of xj, and e taking values of 1 to 1 transpose. So this will be the weight finally. So the primal and dual condition for generating the optimization is that it should not be a trivial solution. There should be some non-trivial value coming out of it. So you can have different encoding schemes for the support vector classification. So for the support vector classifier, we have each data is a vector. So xik, periodically you can have nine zeros, one, then 1 1, then 9 zeros, then 1 1. So you can have 10 binary attributes represented by a quadratic representation like this for ks data. Then xi of k with an integer from 1 to 10. So the one that is better should be selected. So 10 binaries for the support vector classification is better. So x4k more important, including x4 k minus 1, taking dot dot 2 up to x4 k plus 4 for the ks data. So here we find that each of the training data can have many attributes, and for this case, this count may be 22. So how you train it? You first need to do the selection of the parameters. Then you need to select a radial basis function kernel as we have defined it previously. We need to have a Gaussian kernel. So e raised to the with a power raised to -1 gamma, taking a multiplying the norm of the difference between xi and xj, that raised to square. You have two parameters here of gamma and c. Gamma will be the learning rate, and c shall be the convergence term. So we can have five-fold cross validation on 50,000 data, then data randomly separated to 5 groups, and we can have four sets for training and one for the testing part. We can use C as 2 to the power 4 and gamma to the power gamma to be 2b to the power 2, and then train 50,000 data for generating the final model. So here is a case that was used for doing a handwritten digit recognition with the help of the support vector classification, machine classification, support vector machine classification. Now, a general procedure can be you can conduct a simple scaling of the data. Then you can take the real basis function defined by this k of xy, taking the value of e with power raised to minus gamma x minus y norm square. We use cross validation to find the best parameters c and gamma. We use the best c and gamma to train the whole of the training set. Then we need to do the testing. Then best c and gamma can be found by training k minus 1, then the whole. And in theory, a minor difference can be there. and in practice, this minor difference shall not have much of a role to play in degrading the quality. But if the accuracy is not satisfactory, further techniques will be required. So in those further techniques, we find that one of them is the linear classifier. In the linear classifier, as we have seen already, a straight line can be used as a linear classifier, but we can use a signum function too to generate a linear classifier. So here are some of the ways through which we can fix the line and the slope for separating out the regions to have greater reliability and generate maximal separability. So this can be, a number of them can be generated, and then we can have a margin from the linear classifier uh, that will give the width that the boundary could have by could have, uh, and that will prevent misclassification or crossover during the classification boundary laying, and can help in making the recognition performance reliable. So a maximal classification, a maximal separability should be the goal in support vector classification. Therefore, a depiction of this type is necessary. So how to build that part is guaranteed by the support vectors that are generated for each of the classes, and that will guarantee the maximal margin, maximal separability. So why we need maximum margin? The maximum margin linear classifier is the classifier with the greatest maximum margin separation, and this one is the simplest of the support vector classifier, called LSVM. So how to calculate the distance from a point to point? So you can use this Wx plus b is equal to 0, and then find out the gap between this point x and the boundary by finding a distance measure. A very simple case, a very nice solution and a solve problem is shown in this particular site. So I have referred it here. We need to have some means through which we can determine the margin. So the best way shall be to start with Wx plus b is equal to 0, and from there we can determine the support vectors. And the large margin decision boundary shall be linked to this m value given by 2 by a norm w, while the decision boundary for class 1 and class 2 are given by transpose multiplying x plus b is equal to -1 value for class 1, and wtx plus b is equal to 1 for class 2, while wtx plus b is equal to 0 is used for laying the decision boundary. So we can find a decision boundary when we solve an optimization problem such that we find the minimum of a half of this W norm square, subject to the condition that yi taking value of WTXI plus B greater than or equal to 1 for all I. So if that one is guaranteed, then we can find a decision boundary. Then sometimes we need to scale the decision boundary to nonlinear region also, so that we can deal with large margin classifiers and large class problems. So in that case, how to generalize it to become non-linear. The key point here shall be to transform xi to a higher dimensional space to make things simpler. So we need to find here in the input space a point where the point xi are located, and in the feature space we need to have a transformation by the use of a function phi taking value of xi. So then selecting the kernel function is probably the most tricky part of the support vector classifier, support vector classification. So you can have many kernel functions. Not all similarity uh, terms can be used as kernel functions, but kernel function needs to satisfy the Mercer function. That is, the function is a positive definite. That means that you can have a n cross n kernel matrix where the ijth entry in shall be the kth k of xi x j is a positive definite in all cases. This means that you need to have a solution for the optimization problem in a polynomial time. Some of the kernel functions are like this. This is a polynomial kernel k of xy taking the value of x transpose y plus 1 raised to the power of d, degree of d. Then you can use the radial basis function, very popular. You can also use the sigmoidal term. So these are some of the uh, popular kernel functions. Then we also have the nonlinear support vector classification that are used in the feature spaces. So there shall be transformation, since we have situations where in all cases the data may not be linearly separable. Then we need to think about non-linearly separable cases. In that case, we need to do some high dimensional feature space transformation. So here are some of the cases through which we find that there can be boundaries generated for x taking power of 1. This x takes the power of 2. Here we see power of 3. Here we see power of 4. Here we see power of 5. And here we see power of 6. So that way, the decision region boundaries can be separated. There are lots of softwares linked with the support vector classification. One of them is in the website www.kernel machines.org. Then some of the implementation, like the lib SVM, can deal with multi-class classification. Then one of them is SVM Lite, is one of the first implemented. MATLAB also has toolboxes for it. Support vector classification. So we can summarize. Here the steps are like we can prepare a pattern matrix, select the kernel function, select the parameter for the kernel function and the value of c. You can use the values suggested by the support vector machine software, or you can set a separate validation set to determine the values of the parameter. Then you can run the training, and then you can use unseen data for doing the classification and generation of the support vectors. You can consider the support vector classification to be a parallel alternative to the artificial neural networks. Two key concepts of the support vector classification is to maximize the margin and the proper kernel selection. Many support vector um, implementation are there free of cost. They're in the way, so you can try it with your own data set. So that will give you some confidence. So here are many of the resources: machines.org, supportvector.net, supportvector.net, then ICML, and that's tutorial.pdf, kernel machines.org, papers, tutorials, nips.ps.gz, then www.clop.inet.com. So there are lots of resources. When the net, those can be you can view those and then go through them. That will be great. So there we stop today. Then in the next class we will be starting from the regression part. So if you have questions, you can ask. So thank you all. We will meet one more time next Tuesday. Then again on Thursday we shall go on further and then cover new topics. These will be quite beneficial for you all while you learn, and then try to use them for your projects and develop your skills. There we come to an end. Thank you.